we're using idealized primitives, this like special privilege has to be powerful enough to achieve extraction, and at the same time, it can't be something that's too strong or unreasonable. So straight line extractors are a special class of such extractors in which the privilege that the extractor has is restricted to not include rewinding, right? So straight line extractors basically don't rewind the prover. There are a number of reasons why one might want to avoid rewinding the prover. For example, if you want to prove security against quantum adversities, it poses some challenges to rewind. If you want security in the concurrent setting, or if you want a tight reduction, benefit from not having a rewinding extractor. Right, so we look at the random oracle model specifically, which, as a quick reminder, is just an idealization of a hash function. And using random oracles as this sort of special privilege for extraction was formalized by Parse, specifically in the context of straight line extraction. So let's say we have a prover who makes a number of queries to the hash function or the random oracle in its effort to produce a proof. Verifier takes the proof string that the prover produced, checks some subset of the prover's queries, and then decides to accept or reject by comparing these queries with the public random oracle. Now, the extractor reads all the queries that the prover made to the random oracle when it with roughly the same probability that the verifier accepted. So why is this a meaningful trapdoor to consider? Intuitively, it's because hash functions are believed to be complex and unstructured, especially if you're using it to instantiate a random oracle. So the assumption is that if a prover is making meaningful use of this hash function, it also knows the inputs to the hash function that it used. And also, this does line up with a lot of constraints in practice, or rather the way that we instantiate such random oracles is by using well-seeded hash functions. So it's an attractive quality to have in practice. And I want to point out over here that in many situations, even if, for example, you prove security of your scheme using just like collision resistance as a hash function or something, if you were to model the hash function as a random oracle and it permits a straight line extractor, our result still applies. So yeah, it may not be intentional that the scheme has a straight line extractor in the random oracle model. Right, so if you consider protocols to distribute such NISICs, ideally, these protocols should not make non-black box use of the hash function. Conceptually, because if H is a random oracle, then ideally you don't want it to have a circuit description. And practically speaking, hash functions have large circuits, so it's good for distributed protocols to make use of them as black boxes. And for this talk, I'm going to refer to them as oracle respecting distributed protocols, or ORD protocols. And the main insight in this work is basically that oracle respecting distribution is leaky, is inherently leaky in a lot of situations. So if you consider some proof system in the random oracle model, and we assume that we can bound the number of queries that the verifier makes to the random oracle in checking a proof for a given security parameter, and this is an assumption that holds for many natural schemes, then we show that if n is this bound of the queries that the verifier makes, then if you were to try and distribute this proof amongst n+1 provers, like distribute the production of this proof amongst n+1 provers, then any oracle respecting distributed protocol for this task will inherently leak the witness to any n parties. So what this means is that if there's only one honest party in the protocol, an adversary who corrupts all the remaining parties can always retrieve the witness, or rather with noticeable probability can retrieve the witness. So we can't hide the witness from an adversary that corrupts all but one party. So to understand the result, I'm going to introduce this notion of trimming resilience. So let's say concretely the verifier checks two queries, like n equals 2, of what the prover makes. Right? So in this example, the prover makes a bunch of queries and the verifier checks 2 of them. Now consider a three-partitioning of the prover's queries, right? The verifier then checks whatever it wants. And I claim that at most 2 partitions will be touched by the verifier because the verifier only checks 2 queries anyway. So what this leads us to is that if we were to select a partition at random, the probability that the verifier just never touches this randomly chosen partition is at least a third. Right? So we can make use of this fact to maybe reason about things that happen with the extractor. So let's say we consider a malicious prover who does the following. the prover, decides a priori what this partition on queries is. And for one randomly chosen partition, the prover sends its queries to some different independent random oracle H star that's not the same as H. And H star is a random oracle that is a random function that the prover just maintains in its own head. For the remaining two good partitions, the prover stays honest and queries the actual random oracle H. So now let's consider a verifier who's checking this proof. If the verifier happens to touch this bad partition when it's checking queries, there's a pretty good chance that the verifier is going to complain and reject the proof. But if the verifier only touches the good partitions, which made it to the actual random oracle, then the verifier is going to accept and is none the wiser to the fact that one of the partitions is bad. And so we can say that the probability that the verifier accepts this proof, even though one of the partitions is bad, is at least a third. And the point to note here is that the queries to H star never leave the prover. They're all in the prover's head. And so an extractor who is tasked with getting a witness out of the prover can't see the bad partition of the prover because it's only the good partitions that made it to the actual random oracle. And so we can say that the extractor is resilient to this bad partition having been trimmed out. Right? So the extractor should succeed with roughly a probability of 1/3 with just the two good partitions. And this holds for any three partitioning, like it's arbitrary how I label the queries. So in general, we have this lemma that says that for any n+1 partitioning of the random oracle queries made by the prover, omitting one partition will still allow for extraction when we feed the queries to the extractor. And yeah, caveats, this is a randomly chosen partition, and then the extractor success probability does take a hit, but it's still noticeable at the end of the day. So what this means for the context of ORD protocols, so let's say we have our friend Bob again, who's distributed his witness amongst three of his devices. Let's say we have this ORD protocol that runs amongst these three devices. Each of these devices makes some queries to the random oracle, runs some sort of interactive protocol, and they jointly produce this proof pi. Now we know that the verifier checks at most two queries. And of course, the verifier doesn't care that this is the outcome of a distributed protocol. It just does its thing. And what I'd like to point out here is that the set of queries made by each individual party forms a natural partitioning of the overall set of queries that was used in the production of the proof. In particular, if I were to choose one of these partitions at random by choosing one of the parties at random and do the same thing that I did with the trimming resilience thing earlier, and I throw out this party, and along with this party, I throw out the queries that were made by this party. The trimming resilience lemma that I sketched earlier, we should have that the extractor is still able to get the witness out of these two good partitions, of just the views of two parties. So what this means is that two views in this protocol will be sufficient to reconstruct the witness with noticeable probability. And this tells us that any three-party oracle respecting distributed protocol for this proof system will not be able to withstand two even passive corruptions. And in general, we can say that any n-party oracle respecting distributed protocol can't withstand n-1 corruptions, where again, n is the number of queries the verifier makes. Sorry, n-1 is the number of things. There are some caveats because to apply this lemma, we have to take an interactive protocol and then map it to a single-party algorithm. And this mapping introduces one of two artifacts, sort of pick your poison. One could be that one is assuming something about the protocol, which is that each query that's made in the protocol should be traceable to which party first made it. So, I mean, it seems like a natural thing, but of course, this is an assumption on a protocol, and we're trying to rule out the existence of protocols. So maybe you don't want to make this assumption. Alternatively, you could assume that the extractor for the NISIC doesn't actually need to look at the output of the random oracle. It just takes a look at the input queries. Surprisingly, this holds for like many natural schemes. Yeah, and that's fine. And yeah, so what about if there's more than one honest party? We sketch in the paper how you can extend this impossibility to any constant number of corruptions. And we also note that for actual schemes, there are probably much worse barriers to the extent that it's quite likely that you can't tolerate even one corruption for protocols for them. And we also note that you probably can't generalize the impossibility because we show constructively that there is maybe a somewhat contrived NISIC construction that does permit an oracle respecting distributed protocol for any n parties with resilience to any constant fraction of corruptions. Right, so Yeah, in this work, we show that there are certain hash-based NISICs, signatures, specifically those that permit straight-line extractors, that inherently have this barrier to permitting practical protocols to distribute their computation. The barrier being that the protocols can't be black box in the same hash function that they use. And this result applies to a lot of natural constructions, including those that are based on MPC in their head, a lot of these transforms by like Fischlin and Rupas, etc., and PCPs, IOPs, and so forth. And there are interesting questions to think about for future work, such as, like we showed that the NISIC verifier, or rather the distributed NISIC verifier, has to depend on the number of parties. And maybe can we use this insight to maybe derive some sort of lower bound on the size of the proof or something like this, when the proof is output by a number of parties. Anyway, you can find our work online, and I'm happy to take questions.
Thank you for the great talk. Does anyone have any questions? Yes, there's quite a few. We have time for questions, so maybe you could start. And then you...
Thanks a lot, Yash, for the nice talk. I'm wondering how you can make things work for the second type of assumption that you need to add. In the first type, where you assume this traceability, I can see how you can ensure consistency, but I guess you cannot assume that there's no repetition of Oracle queries because of the distributed protocol. So how do you ensure consistency if you replace the Oracle by a fake one for one party?
How do you replace Sorry.
So basically, two parties might make the same query.
Yeah.
And the distributed protocol might abort if they detect an inconsistency. That's
Sure.
what I'm wondering, how you deal with that.
Yeah, so one is the first kind of assumption is that you can trace who made the query first, right? It doesn't need to be part of the thing. So yeah, that's kind of tricky, but like I also want to note that the two assumptions are exclusive, so you make one or the other. So if the NISIC, for example, has this property that the extractor only looks at the input to the random oracle and not the output, then the proof goes through. Like you don't need to make the other assumption about traceability and stuff. As for the thing, yeah, that's true. This traceability thing means that if multiple parties repeat queries, then you need to know who made it first. But that's it for the context of defining the partition, if that makes sense. Yeah.
Hi. So when you make the proof, do you have to assume that each party, when you partition them, make roughly the same amount of queries to the random oracle?
No, we don't have to make that assumption because we have this procedure to map an interactive protocol to the to, let's say, a non-interactive scheme and or like a non-interactive prover. And that mapping kind of handles these artifacts of like difference in number of queries and stuff like this. So we don't have to assume anything about how the protocol distributes queries amongst its parties.
Okay, so assume that all the other parties make roughly n queries. I have one party make like n cube queries, so the proof also works?
Yeah, it's agnostic to that, yeah.
Cool, thank you.
Are there any other questions? Yes.
So the fact that signature has efficient multi-party here. So that's explicit that if you allow rewinding, it all works, right? You can do this with rewinding explicitly. Right?
Yeah, you really need this straight line extraction property, yeah.
Why rewinding is possible? It's possible to do in MPC, whereas.
So I guess with the straight line extractor, because there's an extractor that just takes a look at the queries, that just reads the queries and gets the witness. If you look at the views of the parties in the protocol, they each make some queries to the random oracle, right? And then you imagine I just take, if I'm an adversary, I corrupt some parties and I record which queries they make to the random oracle, and I just feed those into the extractor. And what we show is that with high probability, even if you don't have all the parties' queries, the extractor should still work. So yeah, this wouldn't work with rewinding because yeah, you don't have.
Okay, great. Thank you again. Let's thank the speaker again. And our next talk is going to be about obtaining quantum advantage from one-way functions. This is a paper by Tomoyuki Morime and Takashi Yamakawa, and Tomoyuki will give the talk.
Okay, you're right.
Okay. Okay. Yeah. Okay. So this is a joint work with Takashi Yamakawa. So this is talk about quantum advantage. So first I explain what is quantum advantage. So quantum advantage means the existence of some problem which is very difficult, and no classical efficient algorithm can solve this problem. So no PPT, probabilistic polynomial time algorithm, can solve this problem. But there are some quantum efficient algorithms that can solve this problem. So some quantum polynomial time algorithm can solve this problem. So if such a problem exists, we say that quantum advantage exists. So this is the definition of quantum advantage. Okay. And there are three approaches, previously three approaches to demonstrate quantum advantage. So one is a sampling problem. And second one is a searching problem. And also proofs of quantumness. So now I explain each of them separately. So first approach is quantum sampling. The goal of sampling is to sample some distribution. So I have some quantum machine which output some bit string according to some distribution. And the goal is to sample this distribution. Okay. And of course, quantum machine can do this by definition. Okay. But on the other hand, we can show that no classical efficient algorithm can sample this distribution. So classical algorithm output some bit string, but no efficient algorithm cannot output bit string with some distribution which is very close to this. Okay. Okay. So this is the sampling. And second approach is searching. The goal of searching problem is to find some element that satisfies some relation. Okay. And again, we can show that no classical efficient algorithm can find this element, this answer. Okay. But on the other hand, there are some quantum efficient algorithms that can find this element. So this is a searching problem. And third approach is proofs of quantumness. So this is some interactive protocol between prover and verifier. So verifier is PPT. So this is a classical efficient algorithm. And they exchange only classical message. Okay. And we require two properties. So one is completeness. So if this prover is quantum polynomial time, then verifier accept with a high probability. So there are some quantum algorithm, some quantum prover, which is accepted by verifier. And soundness means for any classical efficient prover, verifier accept only with small probability. So in this way, classical verifier can verify whether this prover is quantum or not. This is the proof of quantumness. Okay. So in this way, we have three approaches. And of course, ideal goal is show quantum advantage unconditionally. So without any assumption, we want to show the existence of some quantum advantage. But this is extremely difficult and beyond our current understanding of complexity theory. So for example, if we can separate BQP and BPP, then we can separate P and P space, which solves one of the long-standing open problems in classical complexity theory. So in this way, unconditionally showing quantum advantage is very difficult. So we have to introduce some assumption. Okay. And then which assumption should we use? Maybe I can introduce my own new hardness conjecture, and then maybe I can show quantum advantage. But this is not so interesting. But on the other hand, if I can show quantum advantage based on some standard assumption, like P is not equal to NP or a one-way function exists, in this case, this is very fantastic. Okay. And verifiability is also very important in quantum advantage. So verification means classical verifier verify that quantum advantage exists. So we have some machine which is claimed to be quantum, and classical verifier want to verify that this is really quantum. So this is really have something quantum which cannot be classically simulated. So this is a verifiability. Okay. So in summary, there are three approaches: sampling, searching, and proof of quantumness. And in terms of assumption and verifiability, previous results are not so satisfactory. So because, for example, for sampling case, we have to introduce some newly introduced assumption, like some Sharpe hardness of computing some value, which was not studied before. Okay, and also we don't know how to verify sampling problem in general. Okay, and for searching case, again, we have to introduce some new assumption which was not studied before, or we have to rely on some random oracle model. But at least for verifiability, we can at least inefficiently verify quantum advantage, because just by doing very long classical computation, we can verify that answer is really correct. Okay. And for proofs of quantumness, assumption is relatively standard. For example, noisy 2-to-1 trapdoor collision resistant hash function, which can be constructed from LWE, or full domain trapdoor permutation, or quantum homomorphic encryption, not necessarily free, but some quantum homomorphic encryption, which can be constructed from LWE, or we can use random oracle. And nice advantage of this proof of quantumness is verification is efficient. Of course, by definition, so verifier is efficient, so we can efficiently verify quantum advantage. Okay, but still, all these results are not satisfactory, and we have the following important open question. So can we demonstrate possibly efficiently verifiable quantum advantage from some standard assumption, like one-way function? Okay. And the main result, so we have several results, but main result of this talk is this one. So we introduce inefficient verifier proof of quantumness, which is some new concept which we introduced in this paper. And we construct this from a classically secure one-way function. Okay. And so unfortunately, this is not efficiently verifiable, but at least this is inefficiently verifiable. And complexity of verification is BPP to NP. Okay. And this inefficient verifier proof of quantumness somehow capture all previous approach. So this is some generalization proof of quantumness. And also somehow this capture this search problem and sampling problem. So now I explain what is this inefficient verifier proof of quantumness. So this is some generalization of proof of quantumness, which I explained previously. So like POQ, we have verifier and prover. And prover is again classical efficient, and they communicate only classically. Okay. So they exchange some classical message, and the transcript is just a sequence of this message. But in POQ, this transcript is evaluated by the same efficient verifier. But here we have another verifier, V2, which can be unbounded time. And this transcript of the first interaction can be is evaluated by this second verifier, And this second verifier makes decision, accept or reject. And again, completeness means there are some quantum prover that is accepted by this inefficient verifier. And soundness means for any classical efficient prover, this unbounded time verifier don't accept. Okay, so one crucial difference is now interaction is efficient, but the final evaluation is done by some inefficient verifier. Okay, so we introduce this, and we construct this from one-way function, classically secure one-way function. And the reason classical secure is soundness is required only for classical prover. So actually, our assumption can be just only classical secure. So we don't need any quantum secure one-way function. Okay, so our construction is based on some proof of quantumness previously introduced by this KMCVY. So they use a trapdoor claw-free function, and they constructed the efficient POQ. So their idea is following. So verifier first generate pair of trapdoor and claw-free function, and this claw-free function is sent to the prover. And prover generate this quantum state by coherently evaluating this function and measure this the last register in the computational basis. Then the state becomes this one, superposition of x0 and x1. So x0 is a preimage of f0 corresponding to image y, and f1 is just its claw. Okay, so in this way, this prover, quantum prover, successfully generate this superposition x0 and x1, and then they exchange some more classical message. And finally, this verifier accept. Okay, and the reason why this is sound is classical prover cannot find both x0 and x1 at the same time because of the claw-free property. Okay, so because this x0 and x1 are claw, and by assumption, they cannot be found efficiently. And by using this fact, we can show the soundness. So no classical prover can be accepted by this verifier. So this is their proof of quantumness. And so now I explain our idea of our construction. So we start with a classically secure one-way function, which is equivalent to statistically hiding and computationally binding commitment. Okay, and somehow I quantize this commitment, which I explain later. And also we combine this with proof of quantumness, which I explained in the previous slide. And finally, we get this inefficient verifier proof of quantumness. Okay, so this is our construction. And now I explain how to quantize this commitment. So this is just a general description of classical commitment. Okay, so we have receiver and sender, both are PPT, and the receiver first generates some random seed R, and sender also generates some random seed X in advance. And this B is the bit committed. And they do some classical computation and they exchange some classical message. And this commitment is just a transcript, which is a sequence of all message exchanged. And the opening is just a random seed chosen by sender. So when sender sends this random seed chosen by him, then just the receiver verify this commitment. So this is just a very general description of classical commitment. And now I quantize this. So now sender is a QPT. Okay, and sender first generates superposition of bit and random seed, this one. And then they run this classical commitment protocol, but this sender does his computation coherently. And in this case, finally, at the end of interaction, he generates this quantum state. So this X is so this state is a superposition of all random seed X that is consistent with this transcript T and committed bit 0. And this large X1 T is just a set of all random seed that are consistent with this transcript and committed bit 1. And now he gets this superposition. And if you remember this KMCVY proof of quantumness, this state is very close to this one. But one difference is this is superposition of many X, But here, what you get is only one single x0 or one single x1. And so if this state is equivalent to this one, just we can run their proof of quantumness protocol. But unfortunately, in general, this is the superposition of many states. And we don't know how to run their protocol from this quantum state. And to solve this problem, and so actually, if this state is the same as this one, just we can run their protocol. And in this case, this receiver corresponds to classical verifier. And this sender corresponds to prover. Okay? But in general, because this is not superposition of this state, so we don't know how to run their protocol on top of this state. And to solve this problem, we introduce this hashing technique. So at the end of interaction, prover has this quantum state, and then this receiver sends randomly chosen pairwise independent hash function H. And this prover evaluates this H coherently, and he measures this register in computational basis. Then the state becomes this one. Okay, so this X is just a superposition of all X, which is in this set plus preimage of this Y. This U. Okay. And now, because of the fact that this is statistically hiding, and also by using some similar argument to variant Bajirani, we can show that the size of this set is equal to 1 with high probability. So this means this quantum state is equal to this one with high probability. And then once this state is obtained, we can run their protocol, KMCVI protocol. So this is a proof of completeness. Completeness is shown. And for the soundness, and for the soundness, if we remember the KMCVI protocol, what they use is a claw-free property. So no classical prover can find this x0 and x1 at the same time because of claw-free property. And now we use classical computational binding. So because of computational binding, we can show that this prover, classical prover, cannot find both x0, which is this element of this set, and x1, which is the element of this set. So if he can find this, he can break binding, because this is a random seed corresponding to transcript T and also bit 0. And this is a random seed corresponding to transcript T and bit 1. So if he can find both at the same time, he can break computational binding. And from this, we can show the soundness of this, our proof of quantumness protocol. So we can show that no efficient prover can cheat. So in this way, we can also show the soundness. And for the verification, unfortunately, this is not efficient. And the reason is in KMCVI protocol, the verifier must compute this value, some preimage of claw-free function. And they can do that because they have a trapdoor. But in our case, there is no trapdoor, and we don't know how to compute this efficiently. But at least this can be computed by doing brute force computation. And we evaluated that complexity is just BPP to NP. So if verifier, the first one is of course efficient, but the second one, if the second one is BPP to NP, then he can verify. Okay, so in summary, we have introduced a new concept, which is called inefficient verifier proof of quantumness, which capture some previous approach. And we constructed this from a classically secure Wahl function, which is a minimum assumption in classical cryptography. And we show that this is not inefficient, but the complexity of the verification is just BPP to NP. So finally, I give some open problems. So first open problem is, can we construct efficient proof of quantumness from one-way function? So far, all known constructions are based on some trapdoor primitive, like a noisy trapdoor claw-free function. And we don't know how to construct efficiently verifiable POQ from a much weaker assumption, like one-way function. Or maybe we can show that this is impossible. So maybe some trapdoor property is crucial, and maybe we can separate efficient proof of quantumness from one-way function. Okay, and also another interesting question is, can we construct even IVPOQ from some weak assumption like P is not equal to NP? So in this talk, we constructed this IVPOQ from one-way function, but the question is whether we can weaken this assumption like P is not equal to NP or something like that. Okay, so thank you very much.
Thanks for the great talk. We have time for one question. If there's, yes.
Of course, with an inefficient verifier, but like here you just used it as a proof of quantumness. Can you also verify that the computation was done correctly?
Sorry?
Can you do full CDQC with this?
Full what?
Can you completely classically verify quantum computation? Here you only used it as a proof of quantumness. It has more general powers.
So maybe we can discuss later, but verify is just entirely classical. So I don't understand what you mean. Maybe we can talk later.
I think the question is, can you verify QMA using these techniques with a classical verifier?
QMA.
Yes, can you do QMA verification with a classical verifier using these techniques? Is that?
Yes.
So you mean verification of any QMA language with efficient verifier plus inefficient verifier? So, but I think already we have classical verification of QMA by Mahadev. So why you need that? A weak assumption. Okay, but okay, maybe we can. I don't have an answer immediately, so maybe we can discuss later.
Thank you. Let's thank the speaker again.